Good afternoon. We are the Waterloo Lightfollowers. Our team is composed by Muhtaram, Ivan, and myself, Humberto. So we made some suggestions into what could be done for the weaker solar suitcase. First of all, we wanted to see if we could devise a solar tracking system that would maximize the amount of energy gathered through the solar panel. Not only that, but we also wanted to see if there could be a way to estimate the time through a time estimate module, which would estimate the time left before the battery runs out, which is of course critical due to the fact that the weaker solar may be used for the medical setting. I'm going to run through the slide pretty quickly. This is a general approach that we took. At the beginning, what we tried to do is to understand the topic, especially the basics. With this in mind, what we did was to research the current state of the concepts, see what kind of methods are out there through journals, critical reviews. And then once we picked the methods that were more applicable, then we compare them in order to find which would be the most robust, cost-effective, and practical. Once we had this in mind, we had the results, we moved on to doing future work. Suggesting future work for the next groups. For the solar tracking system, what we really were trying to look for was an existing practical and reasonable solution in terms of cost. What we found is there was many methods. State of charge is hard to determine. And these methods, one of the ways that they differentiated was by the amount of batteries, the amount of motors that they use in order to track the sun. With this, then we moved on to, we picked different methods and we simulated them through MATLAB. However, we had some difficulties. We found that there's really no standardized dimensions for the panel to work on. Not only that, we also felt like we could be leaning into being impractical due to the fact that we want the suitcase to stay portable, and having a solar tracking system may actually reduce that. Also, there's monetary costs involved in this, and it raised questions on how it is installed, because we might have been talking about how the solar tracking system tracks the sun, but not how it finds the position of the sun. So due to this, we shift our focus really from the time estimate module, from the solar tracking system to the time estimate module, and we made some suggestions for future works. What we really felt like is that our analysis in the simulations may have been basic, and there may be some other analysis that are more deep statistically. Not only that, we also felt like there needs to be a relative importance placed on the cost and effectiveness for the analysis in order for it to work. The aspect that I said before we didn't touch on was how the solar tracking system actually knows where the sun is. So we decided to suggest for future groups to look into sensors and GPS systems that could be integrated into the solar tracking system, which could even reduce the questions of practicality we had before. We also felt like future work could focus itself on what really is the practicality to hardware design trade-off that there may be. Up next is Ivan, who's going to talk about the time estimate module.
Thank you, Humberto. So basically, for the time estimate module, as Humberto mentioned before, we were looking at the basic goal of determining, an estimate for the time left before the battery drains out at any point in time. So what we ended up finding was that in order to do this, we could use an estimate for the state of charge first of the battery, and then combine that with measurement of the current to estimate roughly how much time there's left before the battery drains out. So our problem shifted a little bit towards trying to determine this state of charge accurately. And our first approach, which was very simplified, was to assume that there was a one-to-one relationship between the voltage difference between the terminals of the battery and the state of charge of the battery. But we then found out that it wasn't that simple, because there were some other parameters such as temperature and discharge current and aging, which affected this relationship between the voltage and the state of charge. So what we ended up doing was looking at other solutions which were more complicated. Among them, we found the impedance measurements. There's a method which looks at the impedance of the battery and then correlates that to the state of charge of the battery. And we had some simulation difficulties with this approach, which I mentioned later. We also considered Coulomb counting, which is widely used for lithium-ion batteries and some other chemistries, I believe. But we found there were some conditions, some problems with initial conditions, so we had to do calibration every so often, and we thought it was a little impractical for the application. So we also looked at other methods we used which required very accurate models of the battery, and because we didn't really have that, then we didn't try simulating them or anything. Specific gravity measures, that was also thought to be impractical because you might not have the sensors. They might be practical for the type of like application, because suitcase is portable and that might reduce the degree of portability of the system. And finally, we considered some adaptive measures or some adaptive methods in order to estimate the state of charge, which we will talk a little bit more later. So how did we went about choosing one of these methods? We tried to simulate these methods with a model of the battery, which we found, which was provided by Robin Jackie. He's someone from MathWorks, so he kindly gave us the model, the simulating, so that we could run some simulations and compare the methods. So the basis of comparison for these simulations was basically twofold. We looked at a metric for robustness of the system to make sure that the method was reliable at multiple conditions, and the accuracy of the methods, because we thought accuracy was paramount for this type of application. So, as I mentioned before, so what we did was we simplified a little bit our analysis, and we tried to compare two methods, the most basic ones, the voltage measurement method, and the impedance-based measures. What happened was that we had some difficulties. Basically, as you can see here from one of the simulations, we were always observing zero phase difference between the voltage and the current in the battery, so that didn't allow us to tell anything about the impedance measurement method. Unfortunately, we spent a lot of time doing this. It was really frustrating. So then we tried to simulate the voltage measurements method, and we got some partial conclusions. Basically, we tried to understand how the voltage versus state of charge relationship changed depending on the different parameters that affect this relationship, basically. And what we ended up with was something like what you can see here in this graph. So each line represents one of these relationships, and we calculated, the difference between them using standard methods. And that gave us an idea of how robust the system or the method was. But unfortunately, we didn't have anything to compare it to. But the idea is that some other people can use this approach to compare different systems. So basically, what we proposed was to move a little bit from these methods that we just mentioned into something that's more adaptive. And so you can also account for aging, which is one of the aspects that we didn't touch on the simulation because the model was not sophisticated enough. So we propose to use a Kalman filter approach, which is widely used to observe the state of the system or predict it, estimate it, and also some sort of adaptive algorithm that will refine the model of the battery as time goes on. We also did some research on how we were going to implement these methods, and we're planning on using these pieces of hardware. We found that they were, after doing some research, we found that they were applicable for this type of project, and we estimated roughly the costs of them. So, yes, as I just mentioned, we just provided different methods for comparing these methods, and like highlighted highlighted like our limitations, and gave some recommendations as to the hardware design, how to go about that. So now I'll pass it on to Mugo, who will wrap up.
So basically, to wrap up the presentation, I would like to highlight the significance of the results that we have actually found through our research and our simulations. We have suggested a robust adaptive method that, which will lead us to reliable estimation of the time. And this is critical because this system is being used in medicals, so we thought that accurate timing was very important. Secondly, we have suggested the hardware the hardware we suggested is basically reprogrammable, because it's for the field we have suggested the PEAK microcontroller, which is reprogrammable, it's inexpensive, and